Let's start till I get this thing going, okay? So this is the buttons here? Okay. Okay. I'm pretty good shape. Okay, well, this is becoming a very scary session. First you heard about the blob, and now you can hear about extremes, which is good. You know, there's a lot of interest about extremes. Let's face it, that's where where people are really concerned. That's where the big impacts, okay? And there's a lot of interest, and there's a lot of contradictory information about the frequency of extreme precipitation or weather over the Northwest and how it's going to change. You know, heavier rain, flooding, heat waves, windstorms, drought, snowpack. Everybody wants to know how the extremes are going to change. This talk is going to provide hopefully a somewhat fresh view based on the peer-reviewed literature and the latest modeling research about what extremes will be doing here in the Northwest. Let's start off with heavy precipitation. Okay, there's a lot of concern with that. And the first thing is, what's been the historical change in extreme precipitation here? Well, there's been a number of studies, and I'm going to just show you one or two. This is by Kunkel et al. This shows you the trend of 7-day extremes, 31 to 96. But there's been other studies by Kunkel and others looking at 3- and 1-day extremes. And the stories are always very similar. As some increase of extremes over Washington State, but then as you transition down to Oregon, extremes become less. That's true of Northern California generally, and it's both ways down in Southern California. Very typical. And so the pattern on the West Coast is not uniform. Extremes are not changing in the same ways everywhere along the West Coast. Here's a paper that I was involved in with Mike Warner and Adam on extreme precipitation on the West Coast. We looked at the top 20, 40, and 60 two-day precipitation events, 50 to 2008, and it was a similar pattern to Kunkel. Basically, increasing extreme precipitation over Washington and maybe the very northern Oregon, but actually dropping extreme precipitation in southern Oregon, northern California, and all over the place in California. So if we look at the extremes in top 20, 40, or 60-day precipitation, we see it's actually declining here in central northern California, even North Bend, but in Forks it's going up, and then you're seeing both ways up in British Columbia. So change in extremes is not uniform over the West Coast. And if we looked at the effects of the extremes of precipitation on the rivers, what we find, and it parallels the precipitation, absolutely independent, and that is an increasing trend in the maximum annual flows in unregulated rivers over Washington, but a drop in Oregon. Okay, it's not uniform. Very important. Now, the question you want to know is not what has happened, which has been, it was very heterogeneous. You want to know what's going to happen in the future. Extreme precipitation in the Northwest. Well, to answer that question, you have to answer another thing, and that's what's going to happen to atmospheric rivers under global warming, because our heaviest events, the ones that produce flooding, are inevitably associated with atmospheric river events, which you've all heard about. And here's a paper this is hot stuff. Again, Mike Warner's involved, Eric Salte over here in the front. This is a paper that we've submitted to geophysical research letters. And let me just tell you a little bit. We looked at the latest CMIP-5 simulations, climate models, and we looked at a number of points along the West Coast right offshore, okay? See what was coming in. And the first thing we looked at was integrated water vapor, because the atmospheric rivers are associated with strong values, large values of integrated water vapor flux coming in. And so this is integrated water vapor flux. This is latitude 36 to 46 over here. And this is for the contemporary periods. This is showing the mean precipitation. And this is the extreme over here, 99th percentile. But what I want to show you is that this one over here, 2070 to 2099, the red is the prediction. And what I want you to see is this is a contemporary here. Here's the prediction. And the big story here is the mean goes up, but the extreme values of integrated water vapor flux coming in, driving into the mountains here in the West, that is increasing substantially under global warming. If we look at the precipitation offshore at those dots, And I'll just go to this, the change between, between the contemporary period and 2090, the difference between the blue and the red. It's a substantial increase, okay? So, to give you some more quantitative numbers, the winter mean precipitation on the West Coast, based upon on an ensemble of a collection of CMIP-5 simulations, is that the mean precipitation goes up by 11 to 18% during the wintertime, but the during the extreme atmospheric river event days, how much does the precipitation go up? I mean, we're talking about 15 to 39%, okay? Whether you look at precipitation or the water vapor flux. And just to really impress you, if you look at a certain threshold, the 99% threshold during the contemporary periods, if you go to the end of the century, you're increasing the number of events by about 300%, okay? So there's one other thing I wanted to mention. This is going to be in Mike's thesis. This is really hot stuff. I'm glad he's here. There's a tendency for a shift of the heavier precipitation events earlier in the season, so pushing it more earlier into the fall. And I want to go fast, so I'm going to skip this figure, but basically there's a shift to earlier in the season. So the bottom line in the precipitation is that we got to be prepared for more of this. Precipitation is going to increase. The water vapor flux is going to increase. It makes a lot of sense. The subtropics and tropics are warming up. We're basically juicing up the atmospheric rivers coming in. It doesn't look like the structures will change that much, but the amount of water vapor in them will increase, and that will give us more precipitation. But what about other extremes? About northwest windstorms, right? We're talking about the Inauguration Day storm, the Columbus Day storm, the big windstorms, okay? The Hanukkah Eve storm, okay? Will there be more of them? Will they become more intense? And here's a picture of the Inauguration Day storm for your entertainment. The answer appears to be no. There will not be an increasing trend in such storms. But the first thing you might ask is, what has been the trend over the past half century? Well, of course, there's a paper here in the literature. Myself and Bree Dotson, we looked at major extratropical cyclones along the West Coast. But basically what we found, there's been an increasing number of major windstorms in northern Oregon and southern BC. Kind of parallels the precipitation I told you about before, but it's decreasing numbers to the south. So we're seeing the same thing. It's not, the trends are not the same everywhere along the West Coast, even here in the Pacific Northwest. But the question you want to ask is, what about the rest of the century? Do we expect to see a change in extreme storms? Well, I don't know if anybody from City Light, but we've been working on this, and in fact, we've had a project sponsored by Seattle City Light. A few of the people involved in this are here. And one of the things we've done is looked at dynamically downscaled, that's using the WRF model, versions of global climate models. And we've also looked at wind trends in the CMIP-5 models. And here's a figure. This is kind of fun. 1970 to 2070, okay? This is for a point right offshore, okay? And we're looking at the number of times per year we're above the 90th percentile wind speed for 1970 to 2000, and this is during the winter. So, and the blue is observations, or this is based on the analysis. Well, the basic thing I want you to see is a lot of variability, but there's no trend. There's no trend, my friends, here, going all the way out for this point. Or I can show you that point, Seattle. There's still no trend. Or if you like, or you can see some other points, okay? The other thing we could do is we could look at the change in 10-meter winds for various GCMs, okay? And this is from the HADGM over here. And basically, and in this case, the blues or negatives are weakening, the reds are warming. What I want to tell you is the CMIP-5 models, the latest climate models, are all over the place. Here's one, here's another. You'll see the colors changing all over the place. There's a lack of consistency there. So it really doesn't look like there's any evidence that these windstorms are going to get stronger here, okay? And should we expect there to be a change in windstorms? And I'll suggest we should. There's no reason to expect it. The energy storm for our big windstorms is the strong horizontal temperature gradients that are associated with the jet stream. Everybody knows that. Most global climate models suggest that temperature gradients will weaken in much of the mid-latitudes, like over us, as the Arctic warms up more than the poles. On the other hand, the temperature gradient should increase in the upper troposphere because there'll be warming in the upper troposphere over the tropics. So there may be an increase in temperature gradient to the south of us, so associated with the subtropical jet stream. But that's not what drives our windstorms. One way you can see a little bit of this is going back to the paper that we did with Eric and Mike, was we took a look at the change in 850 millibar winds. This is, again, by latitude, 36 degrees to 46 degrees. This is 850 millibar total wind for the contemporary period. End of century is in red, blue and versus red. They're right on top of each other. There's very little indication. If we look at the zonal wind component in the CMIP-5 model, I'll just tell you that the story is that there's very little change. And in fact, if there's any change in the wind speed, it's to the south of us, and that's the subtropical jet over here. Okay, I'll skip that. Hurricanes hitting the northwest, forget it. That's not going to change. The water's never going to warm up enough here to get hurricanes, so we're not going to worry about that at all. Heat waves, complex story. You're going to hear a lot more about that from Matt in a second. Heat waves, the real heat waves here are associated with easterly winds, right? Offshore flow. Matt Brewer is working on this, and he's going to show you a story, the story in a second, that's suggesting that easterly flow is going to change. One thing I should mention, this is a paper by Karen Babako and Nick and others. They looked at heat waves, and basically looking at the maximum temperature heat waves during contemporary period, there's no indication of the maximum temperature heat waves increasing. It's pretty well distributed through the period. I'll skip that. What about future heat waves? Well, one thing that's not going to change is the cool Pacific is still going to be cool. That's our primary prediction from heat waves. The ocean's going to warm up, but it's still going to be cool versus land. So that's going to help keep our heat waves down. And the decadal trends up to now we have not seen warming of the eastern Pacific at all. That's consistent with the idea that we haven't seen an increase in maximum temperature heat waves. But I'm running out of time, and I want to talk about a little bit what Matt's going to talk about, the strongest easterly winds. The easterly winds are associated with big heat waves. Well, easterly winds change under global warming. And the answer is, and Matt's going to show more of this, the dynamically downscaled models, and this is using the WRF to downscale a global model, suggest that the number of easterly events will weaken during global warming, which would work against us getting major heat waves here in the Northwest. So the potential for fewer offshore flow events might mitigate the potential for having an increase in heat waves. Let me end by saying that there is one critical need for understanding changes in Northwest weather extremes. What we need here is we need a collection of high-resolution, century-long, dynamically downscaled climate runs. This is what we need, and this is what we do not have at this point. It's a substantial deficiency for those of us trying to do climate change, and it's an opportunity. What we need now is to get 10 or 20 of the CMIP-5 climate models and downscale it with high-resolution numerical models like WRF. You have to get it down to 12 kilometers or less to get the mesoscale weather around here, okay? You need bias correction and statistical post-processing. We know what we need to do. This cannot be done by distributed computing on people's personal PCs. I know there's an effort at Oregon State to do that. It just can't work. We need to use heavy metal machines to do these kind of simulations. But these computer resources are available. What we need now is mainly people time. So a big challenge I'm going to put before all of you is if we want to really understand regional climate change in the Northwest, if we want to understand how extremes are going to change, we have to come together as a community, get the resources together to do these regional runs at high resolution driven by large-scale climate models. We need to do this. We have to find the leadership and resources to do it. So let me end with my conclusions. So I'm running out of time. Under global warming, there's the potential for stronger atmospheric rivers and for flooding. So I think that is a virtual guarantee. We warm up, we're going to have stronger rivers, we'll have heavier precipitation and flooding, okay? There's no reason to expect northwest windstorms to become more frequent or intense. No reason whatsoever. Um, this region is going to warm slowly during the next century, and we're going to warm slowly, more slowly than most places, because of the Pacific, because the eastern Pacific is warming up more slowly than almost any place else. And an issue will be the changes in temperature extremes and heat waves. Now, that's going to be moderated to some degree by the Pacific, but a big question is going to be, will the number of offshore flow events change? Because that could really change the answer in terms of the heat waves. And so with that, I'll end and open up to questions. Okay?
Thanks, Cliff. And any questions for Cliff? We can. I think this room is small enough. We probably don't need the mic if you want to.
Yeah, we'll start up there.
You want to point out?
Yeah, go ahead. Yep. Well, I mean, there's several things happened. Clearly, the 1950s was, the 1960s. That was a cooler period, and then when we went through the PDO transition, that was a major shift. Then there's another issue, it's instrumentation changes, and that would also affect T-min. So the question is, how much of the T-min trend is actually anthropogenic? And I think the jury is still out on that. Now, that may be controversial among some quarters, but I think that there is a lot more needs to be done to investigate the T-min issue. Yes, in the back. Sure. Well, I mean, these GCMs aren't the gospel truth, obviously, right? But I mean, one thing Mike Warner did during the last week is he looked at the change in moisture monthly between the contemporary and future periods, and what he showed is during the late summer and early fall, that's where there's the peak change. And so basically, these atmospheric rivers are making use of this water vapor that's around, and the biggest change between contemporary periods in the future is in that late summer fall period. So that'll naturally tend to juice those rivers up then. I suspect that that's a pretty robust answer, but we have to look at more of these runs in more detail. Yeah. So what I'm talking about, when I'm talking about windstorms, I'm talking about the big windstorms, right? The Hood Canal storm, the Inauguration Day storm there. Then we have the other issue about convective storms, okay, which I'm not commenting on, localized winds due to that. And I think this is a fascinating area that we have to explore about how convection is going to change here. And I think that's one thing that's connected with this is the monsoonal moisture during the middle of the summer. How much of that? How will that change? How will that feed of monsoonal moisture change under global warming? And I think that's something that our models have problems with, and I think the answer is still out there. And so those strong winds associated with convection, very limited, but I can't give you the answer right now. Yeah.
Any thoughts about summertime cirrus in Western Washington?
No, not really. You had a question.
You differentiated between the Arctic and the poles.
No. The Arctic region, polar region.
You said the Arctic is going to heat up more
Then the tropics. If I said the poles, I meant the tropics.
than. Okay.
Okay, I misspoke if I said the poles. Yeah.
So this people idea you have of helping do this computation, is this something that citizen volunteer scientists can do, or is it something where you need?
No, no, this is nothing that volunteers or citizens can do. I mean, this is heavy metal computing, you know, done by experts. I mean, that's what needs to be done, to babysit these runs, okay? Yes. Right. So that's a very interesting, issue. I mean, I've been talking. Most of the things I'm talking about are where most of the people are, right, west of the Cascade Crest. It's certainly possible for some of these trends to be different on the other side of the mountains. Let's take heat waves. I think the effect of the ocean, for instance, the Pacific, is much moderated on the other side of the mountains, right? So there's more potential for warm up there. Now the question, we haven't investigated, what about easterly flow in the Rockies? How will that change under global warming, okay? Because that is important for places like Spokane. So we haven't done that yet. I can't tell you the answer to that.
Are any of the science, are any of the climate scientists tracking the fog, the intensity of the fog, the distance inland, up into the river valleys off the coastal streams that are emission, and what kind of prediction?
Okay, the question is about fog. Well, here's an interesting one. I've been talking about extremes. Fog doesn't count as extreme, I don't think. But we have done simulations. Eric has done simulations in which we've looked at the change in low clouds, and in fact, it is possible that you could actually have more low clouds and yes, fog. Let's say in the late spring under global warming than we have now, because what would happen is the interior of the continent heats up more than the ocean. That causes the pressure to preferentially fall. That gives you more onshore pressure gradient. And so you could have more low clouds under global warming west of the Cascades, potentially. So, I mean, there's all kinds of interesting feedbacks that only a full physics dynamical model can help you with.